In this lecture, I will provide you with an overview of regression analysis. The focus will be mainly on how to use regression to analyze a dataset. Therefore, I will not go deep in mathematical background of regression. Same as that you don't have to be a mechanic to drive a car. You can be a good driver without knowing anything about the mechanics of the car. You can read the ECG very well without knowing the details of the electrical changes in the heart. Regression is a statistical procedure in which a dependent variable, y, is modeled as a function of one or more independent variables, which are called x's. The y is called also the outcome variable or the response variable. The x's are called the independent variables, the predictor variables, the explanatory variables. All these names can be given to the independent variables. The general formula or equation is y equals alpha plus b1x1 plus b2x2 plus bnxn. Now, y is the outcome variable. A or alpha is the intercept. The value of y when x is 0. b1x1, x1 is variable number 1. b1 is the slope or the regression coefficient for the variable x1, plus b2x2, x2 is variable number 2. b2 is the slope or regression coefficient for the variable x2, and so on. Of course, this formula lacks an error term, or what we call residuals. We will come to that later on. There are many types of regression. Poisson regression, Cox proportional hazard regression, polynomial regression, hierarchical regression, many forms of regression. In this presentation, I will focus on two general forms of regression. The first is linear regression, the other is logistic regression. Linear regression can be either simple linear regression or multivariate linear regression. Simple linear regression deals with a single independent variable. Multivariate linear regression deals with two or more independent variables. Remember that in both types, there is only one dependent variable. There is an important point that you have to remember. The dependent variable in linear regression must be continuous, and this differentiates linear regression from logistic regression, in which the dependent variable is or must be binary. For simple linear regression, the model is y equals alpha plus bx, where y, or the expected y or the predicted y, is the dependent variable, alpha is the intercept, beta is the slope of the line or the regression coefficient, and x is the independent variable. This formula is very well known. It is the formula for the straight line. The assumptions for simple linear regression: first, linearity. The relationship between x and y is linear. Second, homoscedasticity, or equal variance, similar variance. The variance of residual is the same for any value of x. The third assumption is independence. Observations are independent of each other. An observed value on one person has nothing to do with the value of an observation on another person. The fourth and last assumption is normality. For each fixed value of x, y is normally distributed. What are the uses of regression? First, and in fact, the main purpose of regression is to identify associations between an outcome variable and one or more predictor variables. The second use is prediction of the value of the outcome variable for a given value of the independent variable. This will be explained later. The third is adjustment for confounders. To obtain the effect of a given independent variable on an outcome variable after controlling or adjusting for all other independent variables in the model. The last is forecasting. Sometimes we attempt to predict the value of y beyond the observed values of x. Such attempts should be discouraged, as the prediction or the predicted values are likely to be unrealistic, likely to be wrong. Check the slides that follow carefully. You will see a scatter plot and a regression line. The regression line is drawn using the least squares method. So what is the least squares method? The least squares line is the line associated with the least residuals or errors. The sum of the vertical distances between the observed data points from the fitted line is 0, because these above the line are positive and those below the line are negative. To avoid this, we square the errors, so the negative sign will become positive when we square it. We draw the line so as to keep the sum of these squared deviations from the line to a minimum value, the smallest possible, the smallest sum. The deviations from the line are the errors or the residuals, which equals the actual observed values minus the predicted values. So the total residuals or the total error is the error when there is no independent variables in the model. The sum of the squared distances between the data points and a horizontal line at the level of the mean of y. When we fit a regression line, it eats up some of the squared deviations. So the total error equals the regression sum of squares and the error sum of squares. I hope this is understandable to you. But this idea has to be well understood to be able to understand regression. Any variable will eat up or consume some of the sums of squares. That is the deviations or the square deviations from the fitted line. Note that the regression line or the fitted line should pass through the mean of y and the mean of x. The alpha is the intercept, which is interpreted as the value of y when the x is 0. The beta, which is the slope of the line, it is the amount of change in y for 1 unit change in x. Note that the more the slope of the line, the more is the beta. The alpha and the beta are calculated from the observed data. I will not go into mathematics as I said earlier. The most important item of interest for us in regression is the slope or the beta, as it shows the magnitude of the association between the predictor variable x and the outcome variable y. The statistical significance of the association is provided by the SPSS. Note that if we want the value of y for a given x, all what we need is to substitute the value of x in the equation, which is y equals alpha plus beta x. Just we add the value of x, we know the beta, and we know the alpha. So for any value of x, we can obtain the amount or the value of y. Suppose that our data were height in centimeters and weight in kilograms, and we have an intercept of 23.5 kilograms and a slope of 0.25 kilogram. If we want to know the expected weight for a person 170 centimeters tall, then y equals 23.5 plus 0.25 multiplied by 170, we will have a weight or an expected weight of 66 kilograms for that person. So we can predict the value of y for any value of x. Multivariate linear regression is generally similar to simple linear regression, except that there is two or more independent variables. We explained that earlier. The equation is y, the outcome variable, equals alpha, which is the intercept, plus b1x1, which is the slope of the first variable, and x1 is the value of the first variable, plus b2x2, which is b2 is the slope for the second variable, and x2 is the value for the second variable, and so on. The assumptions for multivariate linear regression are almost the same as simple linear regression. First, the relationship between the outcome variable and the independent variables is linear. Multivariate normality means that residuals are normally distributed. There is no multicollinearity. This assumption is not there in simple regression. There is no multicollinearity between independent variables. By multicollinearity, we mean there is no strong association between the x's. The x's are not strongly related to each other. Homoscedasticity, which means equal variance. The variance of residuals are similar across the values of the independent variables. In multiple linear regression, there are at least two independent variables, which can be of any type. They can be nominal, ordinal, or continuous variables. But let us remember that y, the outcome variable in linear regression, should be continuous. When performing multivariate regression, there is a tendency to add too many independent variables to the model. This is not a good practice. First, it is recommended that the sample size be at least 20 persons for each independent variable. If we have a sample size of 40, we should add no more than two variables. If the sample size is 100, we should not add more than 5 independent variables to the model. Second, we always seek to explain y by the least number of x's to reach what they call the most parsimonious model. The most parsimonious model is the model with the least number of x's that best explain the y, the outcome. So, if addition of a variable resulted in a small reduction of the sums of squares, such a variable is better removed from the model. Again, the intercept alpha is the value of y when all the x's are zeros, just like in simple linear regression. The beta for each independent variable is the amount of change in y for each unit change in x after controlling or adjustment for all independent variables in the model. The r squared refers to the amount of variability in y explained by the model out of the total variability of y, as explained earlier. The total variability of y is the variability in the absence of any independent variables in the model. The higher the value of the r squared, the better is the fit of the model to the data. So the r squared is always used or very frequently used to assess the fit of the model, the fit of the model to the data. This slide shows a scatter plot for percent body fat on the y-axis and neck circumference on the x-axis. Note that the regression line is the line showing the expected values of y for a given value of x. Now, also observe that there is a distance between each of the data points from that line. The squares of these distances from the line are the remaining sums of squares error. The total sums of squares are those between these data points and a horizontal line at the mean of the percent body fat. Some of the residuals or the sums of squares were eaten up by fitting this regression line. This has been explained earlier. Again, this is an explanatory scatter plot showing the regression line and the remaining residual or error, or simply the remaining sums of squares, the sums of squares. after eating up sum of the sum of squares by the x variable in the model. If we add another variable, another x, to the model, we would expect that it will eat some of the sums of squares, and the remaining sum of squares will be reduced. In a perfect imaginary model, there will be no remaining sum of squares, and all data points will lie on the regression line exactly. The slide also shows the beta, which is a measure of the slope of the regression line. What is the difference between correlation and regression? Correlation measures how close the data points to a straight line. It shows the strength of the linear association between two continuous variables without assuming that one of the variables is dependent and the other is independent. Thus, it shows how the two variables covary together. Whether the slope of the line is big or small, steep or shallow, has no effect on the value of the correlation coefficient. To the contrary, regression estimates the slope of the regression line, the beta, and also the intercept, alpha. So it provides the amount of change in y for a 1 unit change in x. This is not provided by the correlation. In regression, there is a dependent and independent variable. In regression, we can also predict the value of y for a given value of x using the formula below, y equals alpha plus beta x. So we can calculate the y for any given x. The bottom line. In regression, we obtain the slope of the line, beta, and the intercept, alpha. While in correlation, these quantities are ignored, and the focus is on how close the data points are to a straight line. Now we come to logistic regression, after we finished linear regression. Logistic regression is a statistical technique to model the relationship of a binary variable y with one or more independent variables. The independent variables can be of any type, continuous, ordinal, nominal, whatever. But the explanatory variable, the y, should be binary or dichotomous. Yes, no. Dead, alive, or alive, dead. Sick, not sick. The general equation is y equals alpha plus b1x1 plus b2x2 plus bnxn, where the y is the ln odds ratio. Ln odds ratio. Alpha is the intercept representing the value of y when there is no independent variables in the model. B1 is the slope for x1, representing the ln odds ratio for 1 unit change in x1 after controlling for the other independent variables in the model, and so on for the other independent variables. The same equation can be written as follows. Ln P divided by Q equals alpha plus B1x1 plus B2x2 plus Bnxn. Ln P divided by Q. P here is the probability of having an event. Q is 1 minus P, which represents the probability of no event. We can also write instead of it ln odds ratio. Ln odds ratio equals alpha plus b1x1 plus b2x2 plus bnxn. Sometimes ln pq is referred to as the logit of P or logit P. To predict the probability of having the event given one or more independent variables, we can modify the equation as follows. P, which is the probability of having an event, equals 1 in the numerator divided by the denominator, which is 1 plus exponential minus alpha plus b1x1 plus b2x2 and so on. The odds ratio for x1 is exponential beta 1 or anti-ln or anti-log beta 1, because beta 1 is the ln odds ratio. So if we want to know the odds ratio, we just take the antilog or the exponential. So what is ln that we used in the previous equations? Ln stands for the base of the natural logarithm, which equals 2.718. It is an irrational number, so that the decimals are endless. Note that E stands for the antilog or the exponential. To understand from where we got this base of natural logarithm, it is in fact the limiting factor, the value of x that limits the value of x that limits the following expression: 1 plus 1 divided by x to the power x. If we increase the value of x, the value of the above expression increases until we reach a value of x, beyond which the value of the expression will not increase. this value of x is 2.718 and so on, because it's an irrational number, which is the base of the natural logarithm. In other words, the base of the natural logarithm is the value of x, which limits the value of the above expression. This slide shows the it shows the logistic function, which is S-shaped. Now, y is either 1 or 0, present or absent. This is why we use ln y, ln odds ratio, instead of the y itself, to make the association between the outcome variable and the x's, or the independent variables, linear. It will become linear if we take the ln, not the actual value of y. This is why we use the ln odds ratio as the y rather than the actual value of y, to make the relationship between the y and the x's linear. This slide has already been explained. The outcome is either 0 or 1. The logistic function is S-shaped and not linear. And this is the basis for the ln transformation of the y, or outcome variable, as explained earlier. I am sure we will find a way how to practically apply regression, whether linear or logistic regression, in SPSS. I also want you to see many YouTube videos on regression by somebody called Brandon Foltz. Very nice, very informative, very simple videos by Brandon Foltz. Also, there are many videos on how to perform linear regression and logistic regression using SPSS in the YouTube. Let us keep in touch, and if you did not understand anything, if you don't understand anything in this presentation, please call me by telephone, and I will be ready to explain everything. Thank you.